Hi there, my name's Andrew Brown. Welcome to Real-Time Music and Sound with Pure Data. In this episode, we're going to be looking at additive synthesis. You've possibly seen a waterfall diagram like this, a spectrum of sound over time. The thing to notice is that there are these ridges in the graphics. Those ridges are harmonics or overtones of the sound. And you can see that the complex sound is made up of a number of overtones. On the axis going back and forward is time, and you can see that the overtones fade out towards the end and that they change by different amounts, which adds a lot of complexity to the sound. So in additive synthesis, we're going to create each of these ridges individually and then sum them together. This is a simple graph of what we're going to produce. We're going to have a number of oscillators and they're all going to be summed together. Each oscillator has its own frequency and its own amplitude. And it'll be the balance between these, both the frequency ratios and the amplitude levels, which will control the timbre of our output. Okay, let's get started. We're going to start with a simple oscillator. I'm going to use a number box to control the frequency of that oscillator. And we're going to pass the output of the oscillator through a multiply tilde, which is going to control the volume of this particular oscillator. We use another number box to specify the loudness of the amplitude. I'm going to change the properties of this output box so that the lowest volume level will be 0 and the highest volume level will be 1. This is just a safety measure really to make sure I don't turn that up too loud. The output of that will go to a DAC tilde object, which is the digital to analog converter, which sends our sound out. So if we increase our frequency, let's do that by integers, and then we increase our amplitude, we can see that we've got a simple sine wave oscillator operating at this frequency. So that's one of our overtones. With additive synthesis, we need to add a few of those together. So let's copy and paste that to get a second oscillator. We need to sum those together. So I could disconnect it to the DAC, but what I'm going to do in addition is to put an extra volume overall kind of master volume control in place so that we can control the overall volume of all of them. I will again set the properties of that. So I connect the output of each of our oscillators to our master volume control, set all of these up. So there's our first frequency and there's our second, and you can see that as we add the second one we get a change of timbre. We can change the frequency of either of these. That also affects our timbre as well. So this is the beginnings of our additive synthesis process. Normally what we want to do with additive synthesis is to keep the ratio of these oscillator frequencies consistent as we change frequencies. So I'm going to set up in a sense a master frequency number box up here, and then I'm going to provide a multiplier for each of these oscillator frequencies. The first one is just multiplied by 1, which is possibly unnecessary, but it just demonstrates the point. And then for the second oscillator, I'm going to multiply the base frequency by 2. So this means that the second oscillator will always be twice the frequency, or an octave above the first oscillator. So if I change this volume, so I get 120, this is 120, and the second oscillator is 240. We can hear that as I change the frequency, we maintain a consistent timbre because the ratio between these oscillators is the same. If we vary that ratio, for example, control this one directly, then we do get a timbral change, but because they're locked in here, you can immediately get that back. So this is the basis of what's going to be our additive synthesis architecture. So I'm going to add a few more of these. Third one, fourth one, and say a fifth one, and then connect them all up. So this particular overtone will be 3 times the base frequency. This one will make 4 times, and the next one we make 5 times. By using simple ratios like 2, 3, 4 and 5, we guarantee that we're going to get a harmonious kind of timbre, if you like, a consonant kind of timbre. If these were other frequencies than simple ratios, then we would get a more dissonant timbre. So turn that up. We can set the frequency, and you can see that when we change this master frequency, all the other frequencies change. Then we can bring in the other harmonics, and so as we change frequency, we maintain a consistent timbre, and as we change the values of these different partials, we change the timbre. It's typical in additive synthesis that the fundamental frequency is usually the loudest, so it's 84% in this case, and then each subsequent one is slightly less. This is the kind of pattern that naturally occurs in many natural sounds, acoustic sounds. It doesn't need to be that way, but this will produce a much more natural sounding outcome. So by doing this, we can add as many frequencies as we like. We can change the timbre to be whatever we want, and then that timbre will track across the frequency range because we're doing this multiply of that fundamental frequency. And so that's the basis of additive synthesis. See you later.